guys, I'm Whitney from Knitronics, and I'm back with my video tutorial series on getting started with FPGA design, specifically using the Xilinx tools Vivado and focusing on the Arty Z7 from Digilent. I chose this board because it's a pretty simple board to get up and running with. A lot of the concepts for actually setting up the Vivado project are the most straightforward they can be out of a lot of these boards. That being said, I can definitely understand that setting up an FPGA project in Vivado for the first time is very daunting, thus probably why you clicked on this video. So let's get into it. So one of the perks about using a development board such as the Arty Z7 compared to picking out your own FPGA chip, laying out your own PCB, laying out your own peripherals, is that a lot of the existing design is available for you to implement in Vivado so that you can cut straight to actually putting in your own custom design rather than redoing all the connections for the Ethernet that's on the board or these Arduino header connections or the HDMI. So when you launch a new Vivado project, you can choose to target a specific development board. Now in Vivado 2021.1, like we're using today, that's changed quite a bit compared to how it used to be. Prior to 2021.1, you'd have to manually go download your own board preset files from whatever vendor your development board was coming from. So in this case, the Arty Z7s from Digilent. In the past, we would go download the board preset files from Digilent, install them in Vivado, open Vivado, and then create our project. However, Xilinx has actually integrated a lot of those repos directly into Vivado. So let's jump into it and I'll show you. So we're gonna start by sourcing the Vivado tool set in our environment. So source tools Xilinx Vivado 2021.1 settings. It's our settings script, and then we'll run the Vivado command to launch the Vivado GUI. So once we get to our Vivado landing page here, we're gonna do create project. And starting through next, we're gonna name our project. So I usually like to name my project either the specific project name or something about the dev board I'm using. I have weird OCD naming convention things. I'm sure you all have your own thing. So I'm gonna name this Arty Z7 2021-1, or I think it has to be underscore. I don't think you can use dashes in here. So I'm just gonna leave that in my home folder, create the project subdirectory. This will be an RTL project. I'm not gonna specify my sources at this time, so I don't have any like custom VHDL or Verilog files to source at this time. For right now, this is not gonna be a Vitis extensible platform. That's more reserved for if you're doing accelerated applications like machine learning applications, or specifically if you go back to my Kriya unboxing, I explained a little bit there where you'd be creating accelerated applications for it. We're not doing that. This is just a plain old Vivado project that we're doing for this board. So now we get to our next screen where we choose either the target FPGA chip or the target FPGA development board that we're using. By default, you're on the parts screen, so we're gonna switch over to the boards tab. And this is where things are a lot different. So right now, Vivado is actually looking at a repository that Xilinx has made on the back end called XHub, or the Xilinx boards store. I pulled it up separately here. So, Xilinx board store. So this is the GitHub that Vivado is actually pulling from. So I just discovered this. I'm not sure how this would look as far as adding your own custom one, or if you maybe have an FPGA development board with board preset files already defined. I'll have to figure that out another day and post another tutorial, but it looks like Xilinx already includes Avnet, Digilent, Trends, and their own boards. This pink ZU, I'm not sure what this one is, but it's not what we're looking at today. So we're gonna come back, and looks like to fetch the latest available boards, there's a refresh option here. Here I have the Arty Z7-20. Maybe be easier. There's a search function. So Arty So there's the Arty A7, which is the Artix base. So here's the Arty Z7-20, which is the development board I have here today. Oh, so we directly install it. So let's click install here. Has been installed successfully. So scroll back to it. So if I click on it now, oh, didn't need the, must have clicked on something wrong. There we go. So now if I select it again, oh, there's our next button. Next, and then we just get a nice little summary of the project we're creating. So we're creating a new RTL project titled Arty Z7 2021.1 and targeting the Arty Z720 board. So finish. There we go. We have our blank Vivado project. So the first thing to do in any Vivado project is typically we create a new block design. So we'll select create block design from the project manager over here. You can name it anything you want or leave it the default. So we'll do Arty Z7 BD for block design. Click OK. And here is our blank block design. So in Vivado, if you're not familiar, there's two ways to instantiate IP cores or Verilog or VHDL code. You have the actual block diagram where a lot of the IPs are represented as block GUIs and you can connect them that way. And you can also import in actual RTL modules. To instantiate the ARM core and the Zinc processor, you have to create a block diagram. So that's going to be the first thing we add is we're going to hit this search button or the add button and search for Zinc. Double click. We're going to add the Zinc processing system, and you'll notice that immediately we get a little run block automation option to pop up here. This is one thing that I really like about the Vivado toolset is as much as it can do automatically for you, it will try to. So like I said, there's no point in reinventing the wheel on connections that you can't change on this PCB in your design. So for instance, how the FPGA is connected to its flash memory or its DDR, you're not going to change that. So that's part of what this block automation is going to run for us. So if we click on the hyperlink here, you'll notice apply board preset is an option. So it's going to go ahead and configure the Zinc IP chip the same way that it's been mapped out physically on the Arty PCB. Click OK. We'll let that run. Okay, and there we go. Now we have our Zinc instantiated in our design. Therefore, we now have access to the ARM cores that are on this chip to program and configure. So our next thing is we're going to start selecting what peripherals, what hardware peripherals on the Arty board that we want to include in our design. So that's where, if you look in this little window here, there is a tab called Board. I really like this. This is where this is part of where the board preset files are coming in. You'll see I have listed everything here that is available to connect to the FPGA on the Arty Z7. So it is worth noting that there are some peripherals on the Arty Z7 that can't all be connected at the same time. They are using shared resources in the FPGA. So to start connecting the things you want, you'll just start right click. So like on system clock, we'll right click. We can look at board component properties down here, or we can select, we're gonna connect the board component and we want to connect it to our clock in 1. So click OK, and we will let that generate. So that generates our clocking wizard IP and then connects the system clock pin, which is the actual crystal oscillator on the board to it. You'll notice we have a connection automation pop up here. So let's go ahead and run that. And that's just going to connect our reset pin to our clocking wizard. And then this little circle is a regenerate layout where you can kind of keep the block design looking nice and visually manageable to you. So I've got the system clock and the reset lines connected. I think I want to add, so I can add anything from here we've got 2 RGB LEDs, which on the board, yeah, so we've got, so the RGB LEDs, so that's LEDs 4 and 5 here on the board. We've also got 2 switches, so that relates to SW1 and SW2 here on the board. 4 buttons that we could choose from. And then our 4 LEDs located above those buttons. And then our shield pins, which are referring to the Arduino header layout we have here. So I'm just going to connect, so right click on the switches. We can also do auto connect. That will just go ahead and default connect the switches to a AXI GPIO block. So click OK. And then notice our connection automation is going to pop up again. So if we, oh, that is one thing. If Vivado is still thinking about something and you're clicking too fast, sometimes you'll get these little background task things. Don't worry about it. Just click OK and maybe wait a second. This is going to connect the AXI bus on the GPIO back to our Zinc processing system. So we'll click OK. And then let's regenerate our layout here to make it look a little bit cleaner. And then now I want to connect my 4 LEDs. So I'm going to right click, and instead of auto connect, I'm going to select board component. So you'll notice that auto connect just by default connects using the first option, but sometimes some of these peripherals, you have different options of what you could connect them to. So for instance, the LEDs could connect to an AXI GPIO port, but you could also connect them to a microblaze GPIO or a timer. I'm going to stick with the AXI GPIO. I have the option to create a whole new AXI GPIO IP, or I can go ahead and connect it to the second channel of the AXI GPIO I already have the switches on, which is I think what I'm going to do just to save resources here. And then, so I've also got I2C on J2. So I think J2, that's our Arduino header. So yeah, that's giving us our I2C just like you'd have in an Arduino Uno header. And then we've also got our 2 PMOD ports. So now when you get to this point, you'll go ahead and I like to regenerate the layout just to keep the block design looking nice, just from a conceptual mind. And then we're going to validate our design. So validation successful, there's no errors or critical warnings. That's typically your goal. In Vivado, there are 4 different levels of information that you're given throughout the project. There is just your plain old little info messages, just they kind of tell you what you've been doing throughout your project. When I'm really stuck debugging and I think I might have just clicked on something wrong or done something stupid, it's kind of helpful to go back through the info messages and the log and read back through those. The next level above infos are just plain old warnings with the little yellow icon. Warnings are just things like, say you have a 16-bit bus, but you've only connected 8 bits of them, and that's perfectly acceptable in a design. That may be how you want that design to work. However, you will still get a warning just letting you know that those other 8 bits are unused and unconnected. Like I said, if that's something you did on purpose and you know that your design's working otherwise, you can ignore that warning. And for the most part, a lot of FPGA developers using designing tools, me included, I typically ignore just plain warnings, just because they're basically just like that. It's more of just a by case basis. But like I said, if you're really stuck in debugging something, it's good to come back and you can start looking through the warnings. The next thing above warnings are critical warnings. So these are things like timing violations or things if you have your skew is off. These are critical warnings you don't want to ignore. Those are something you need to take the time to actually go back and fix. And then as well as right above critical warnings, you have your errors. And errors are your absolute showstoppers. You can't generate a bit stream, you can't go any further. So those will be things like if you don't have any constraints and you try to generate a bit stream so your signals don't know what pin on the FPGA to go to. But we'll dive into all of that stuff a little bit later. At this point, we're gonna click OK on our valid design. and we're gonna save our block design. And so once you'll see the little star disappear, you'll come back to the sources tab and see that there's no little running update thing. Now that we have the block design actually done and the Zinc IP instantiated within the block design, we need to instantiate the block design itself within the overall design. And that is done with a top-level HDL wrapper in Vivado. So to create that, we're going to right-click on the block design in the Sources tab and hit Create HDL Wrapper. There's two different options. You can either manually update this HDL wrapper, so if you come back to your block design and you add things that have external I/O ports, you'll have to manually come back to your HDL wrapper and add those into your code, which is why personally I like to let just Vivado manage and update it, so that's what I'm gonna choose for now. And we're gonna let that generate.
A few moments later.
And you'll see now we have our top level file. We're gonna double click to open this from our sources window. And you'll notice it's highlighted in bold. So whenever you have a bunch of HDL files in the sources window, the one highlighted in bold is your top level root file. Like I said, you always have to have a top level root file to instantiate your block design with. So I have my project settings in Verilog, so that's why this was generated in Verilog. You can come up in here into settings, and under general, you can change target language to VHDL. So if you did that, your wrapper would be generated in VHDL instead. As you can see, it's got all of our external I/O, such as all the connections going to the DDR, the I/O, our LED bits, and our switches, and the system clock, and it's got that all instantiated, and then our actual instance of the block design here. That's gonna be all for this tutorial. We've got our base design in Vivado going now. Stay tuned for the next video in the series where we're really gonna talk through the actual design flow of synthesis, implementation, and generation of a bit stream, and really dive into what those mean. So, catch you next time.